I've always been a big fan of night photography, but I really hate driving hours out to a spot only to get there and realize that there's too much light pollution to take any good shots of the sky. So today I want to take a look at generating an interactable light pollution map. The first thing we need for this project is an interactive map. So I set up an Earn environment and got Leaflet React up and running. Here's what that looks like. Since we'll be working on a stargazing app, I'd like the map to have a nice night theme. Unfortunately, Leaflet doesn't really have one built in, so we're going to have to make it ourselves using CSS filters. But luckily for us, it's not actually that hard to do. All we have to do is invert the colors and rotate the hue so our water doesn't end up brown. Here's what we ended up with. With our map all set, we need to figure out how we're going to get the lighting data to make our light pollution map. I ended up using an image of the Earth at night provided by the kind folks at NASA. If you want more recent data, the Colorado School of Mines does an annual mosaic, but you need an account and I didn't want to bother with that. You might have noticed there's a glaring issue with this image. There's no way these two maps are going to line up. That's because they were created using different projection models. We can fix this, however, with a lovely library called GDAL. Because our image is a geotiff, it has Earth data attached to it. This lets us modify the image using that data as a reference. If we use the GDAL warp command in our terminal, we can make the equirectangular map Web Mercator instead. Now that we have our light data, we can start writing our algorithm to emulate light pollution. We have an important requirement to consider first. The image we're working with is absolutely massive. We need to make sure whatever algorithm we write is performant. My first attempt went very poorly because I didn't account for the number of pixels in the image, and I wrote something so awful that it would take 20 days to a year to run. I don't know about you, but I want to avoid this if possible. We'll be using OpenCV and NumPy to apply a modified linear light fall-off formula to a grayscale of our image. First, we're going to make a normalized copy of our image as a float32 NumPy array. Then we'll get all the coordinates of all the hotspots in the image. Hotspots are any pixel that are not black. We're going to iterate over this collection of hotspots. For each hotspot, we're going to be checking pixels within a 400 pixel area to see how it will be affected by our current spot's light. To do this, we'll need to get the distance between the hotspot and the spot we're checking. We'll then use that distance and the hotspot's intensity to apply our light fall-off formula, which is intensity divided by distance times 1.5. However, since we're checking pixels in the same pattern every time, we don't actually need to calculate our distance and light fall-off every loop. Instead, we're going to pre-compile these values, store them in memory, and access them during the loop. Our only value that changes every loop is intensity, so when we store our light fall-off values in memory, we'll instead use the formula 1 divided by distance times 1.5, and then we'll scale that by intensity when we retrieve it. This operation gives us how much light is being casted on the selected pixel by our hotspot. We'll take the casted value and check if it's greater than the selected pixel's current value. If it is, it replaces the old value. Once we run this algorithm and save the result, we now have a map of light pollution. Here's an image I generated that we can use to showcase our changes. This is what it looks like before we apply our algorithm. This is what it looks like after. The image looks a little plain without any color, so we're going to apply a color ramp to give it a little sizzle. Now we can see it's a little blocky, so I want to apply a Gaussian blur to smooth it out. I ran the same operations in our nightlights image, and I'm quite happy with the results. Now we just need to display it over our world map, and oops, I should get rid of that warp. Much better. We can tell that our two images are lined up by looking at the locations of towns. And as you can see, all the towns have light pollution around them, so it looks good to me. Now, as far as how accurate this light pollution map is, I'm not really sure. I mean, I've been to some of the places on the edges of light pollution and it looks like it lines up to me, but I wasn't super scientific about it. I'm happy with the results though. Now we're going to add just one little last feature to our program. I want the user to have the ability to click on a spot on the map and then get the spot's coordinates. Overall, I think this project turned out rather nicely. Obviously it has some glaring issues, performance being a big one. In the future, I'd like to see about tiling the overlay image and then performing some culling on it to speed things up. There's also a back end to this project that I didn't use at all. I'd like to add some features that utilize it, maybe weather prediction for a selected point or upcoming celestial events, but I think that's all for now. Maybe next time.